Well, hello, PreCal students. I know this is the time you've all been waiting for. We get to finish Chapter 5. We're going to look at Section 7 of Chapter 5. Last time we were together, we talked about the Law of Sines, and so it's appropriate that today, as we finish this chapter, we talk about the Law of Cosines. And so that's what we will do. So first of all, I want to just kind of, again, give you a quick explanation as to how the law of cosines was developed as a theorem. Note here, we've got a particular triangle that's set up. This triangle is set up with one of its vertexes at 0, 0 at the origin of the coordinate plane. We see then B out here at the point C, comma 0 if we make this distance, this side length, be C. And then note that point C up here is then just the point xy, because whatever far we have to go over x and however high we need to go in y, that's the point C. So we have a triangle here, ABC, bounded by that. Now notice what has been done then to the rest of this. If we have sides A, B, and C, we could further divide side C in accordance with the perpendicular, which would show its height here being drawn. We could call this part of that x, and we'll call this part, the remainder part, c minus x. Now, the reason why we've done that is so that way we can set up this next formula. We know if we look at this now green triangle here, that we can say, again, if this side, c minus x squared plus y squared has to equal a squared. And so that's what we've written here. A squared equals this side squared plus this side squared. Okay, so now with that in mind, the rest of this is just going to be algebra. So let's look at it together. So here's the proof worked out then. So we have a squared equals c minus x squared, quantity squared, plus y squared. Well, if we then next go ahead and FOIL this, we will get c squared minus 2cx plus x squared. Now, it's at this point that we need to get rid of the x's and y's. And so we have to think about what's a way in which we can describe x in terms of values that we already have, terms of a, b, and c, terms of sines and cosines of angles. So if we look at that for a moment, we can realize that x, if we look from this angle, angle A, that x is just b cosine angle A. And then if we're looking for y, well, y is then, remember, just opposite here over hypotenuse. So y would just be b sine A. Now we're going to substitute both of those things into the equation here at the left. And so wherever I see an x, I'm putting b cosine A. Wherever I see a y, I'm putting b sine A. And now, again, we just do some grouping here. We'll have c squared minus 2cb cosine A. But then if I take out the b squared, notice that the square will get distributed. So we have b squared cosine squared A plus b squared cosine squared A. If I factor out a b squared from both of those, notice what I have here. I have cosine squared plus sine squared, which we know equals 1. And then, as a result, we're left with a squared equals c squared minus 2cb cosine A plus b squared. Or we could rewrite this as a squared equals b squared plus c squared minus 2bc cosine A. So what's really great about the law of cosines is that now we have a law that works even for triangles that are not right triangles. Remember, a squared plus b squared equals c squared only worked if we had a right triangle. But the law of cosines works with any angles within the triangle, as long as we have the angle of the side that is opposite the one we're trying to discover. Notice here that if I have a triangle like this, this angle A, I'm trying to discover this side. So I need to know B and C. I need to know this angle measurement. But if I have those three, I then can find out the length of that side. Note that this is the kind of triangle where we have side, angle, side. We have side, angle, side. When I have that situation, I can now discover the other side, the opposite side of the angle A, through the law of cosines. So we can rewrite the law of cosines depending on which side we need. So just notice here, a squared, if we're looking for this guy, we need to have the angle opposite it and the two adjacent sides. That's how we would be able to get to the A. But similarly, if we didn't know B, we would need to know the angle opposite it and the other two adjacent sides. And if we needed to know C, we'd need to know the angle opposite it and the two adjacent sides. So as long as we have the angle opposite and the two adjacent sides to that angle, we can discover the other side, the opposite side, through the law of cosines. All right, so let's just work a few problems with this formula. Again, you're going to write this down on your sheet, okay, guys? So you can have it with you on the test. I'm not expecting you to memorize all these formulas. So you write this down, add it, and include it in your identities and laws, and we're just going to use them together. All right, so for solving triangle ABC, remember what we're doing whenever this happens. We're discovering any lengths of sides we don't know. We're also discovering the measurements of the angles that we don't know. So in this case, we need to know angles C and B, and we need to know the length of side A. So the first thing we're going to do is just recognize here that we have a great case for law of cosines. Note here, we have a side and an angle and a side, and they're all together. So it's side, angle, side. So that's the perfect case to use law of cosines. So we're going to use this. A squared equals B squared plus C squared minus 2BC times the cosine of A. And so now we just plug in all the values. 12 squared plus 9 squared minus 2 times 12 times 9 times the cosine of 23. Do remember, guys, you have to make sure that your calculator is in degree mode when you type this in. If you're still in radians, you're going to get problems. So make sure that you are in degree mode when we're taking cosines of a degree measurement. And if you do that, you'll get a squared equals this. And so then we just take the square root, and we get roughly 5.1 feet. Remember what I told you last time? We can also check for reasonableness, and again, looking at this triangle, it seems to make sense that this should be the shortest side, right? Because this angle appears to be the smallest angle of the group of three that are here. So the longest side of a triangle is opposite the largest angle. The shortest side of the triangle is opposite the smallest angle of the triangle. All right, so we got 5.1 for A, but we haven't finished, right? We still need to find C and B. Well, how will we go about doing that? Well, you have a couple options at this point. Now that you have all of these, you have all sides and you have an angle, you could use the law of sines, but you could also use the law of cosines again. So if we use the law of sines, we would just pick here in this case, sine C, and then remember the side opposite is C. This would be 9. And then we could use, again, sine of 23a here over the new number that we just got, 5.1. Notice what we're doing here is we're trying to keep as many decimal places as possible and rounding at the very end. And from that, you'll find out that you get sine of C is 0.6874, and then you use that arc sine button on your calculators, sine to the -1, and you discover you have 43.4 degrees. And then in order to find the other measurement, all we do is we subtract both those angles from 180, and that will give us the remaining angle here, B. So also just wanted to show you that you can go about rewriting this law of sines to solve for the angle measurement. All we're doing here is we're subtracting the B squared we're subtracting this part over to make it positive, and then we're subtracting this guy over this way, making it negative, and then we're just taking this part and bringing it underneath, which is what we have here. So if we're solving for the angle, this is a way in which we can do that. And obviously you could do it for the other angles as well. That's just basic algebra. So if I have a case in which I'm given all the sides, this is like a case of side, 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 right? Where I've given all three lengths of the sides of the triangle, but no angles. Again, I can use the law of cosines to discover one of the angles. I can say cosine G is f squared plus d squared minus g squared over 2fd. And plug in all of the pertinent information and get this number. Then take the arc cosine of negative 0.3125 and get an answer of 108.2 degrees. Well, knowing that, we can now do the law of cosines again. Or you could do the law of sines if you rather. Once you have all three sides at an angle, you can use the law of sines if you rather to use that. Or you just use the law of cosines again. Again, plug in all of the pertinent information and get out an answer of 22.3 degrees. And then for the remaining angle, again, you can do law of sines or law of cosines, or you can just take 180 and subtract 108 and 22.3 from that and get the remaining angle. All right. Again, this is a case in which we just have all three sides. But I want to note this kind of special case. Notice that here A is said to be 12, B is 4, and C is 3. Now, think about this for just a moment. If I have a triangle, and I'm telling you that one side is 12, one side is 4, and the other is 3, does that even make sense? In other words, if I was to draw this to scale, which is hard to do maybe right here, but let's imagine that this is 12. Half of 12 would be 6, right? And half of that would be 3. So imagine I have a side that's about 3 inches long, or 3 units long. And then I have another one that's 4 units long. And I have to connect it with the end of this. Well, if it's 4 long, I probably have about that far. And it doesn't make it all the way to the end of this triangle. In other words, these sides cannot describe the sides of a triangle because they can't fit together. So what would happen if I went about trying to do the law of cosines on this? Well, I put in all of these answers, and I would get 1.903. Now, what's the problem if I say that cosine of beta, or b, equals 1.903? Well, you should remember from our previous discussions that cosine can only range from -1 to 1. And this is beyond that. So if you try to take the arc cosine of 1.903, you'll get an error message. This is not a triangle at all. And this is because any two sides added together must be greater than the third side if it's to be a triangle. So when I pick B and C and I add them together, I get the value of 7. But that's shorter than the other side of 12. So whenever you add two sides together, they have to be longer than the other side in order for it to be a triangle. Otherwise, it is not a triangle. Okay, so now the book also in the next example problem has a triangulation of location problem in example 3. But before I talk about that, I just want to make sure you understand what a bearing is and what we mean by compass measurements. So standard position that we've been learning together with the unit circle and all of that starts with our 0 degrees going here to the right along the x-axis, and then we travel around this way to get eventually all the way around to 360 degrees. But whenever we're talking about compass bearings or headings, north is considered the 0 degree measurement, and then we travel around this way to get to 360. So note here, we're traveling clockwise, whereas in this case, we're traveling counterclockwise. And also note that the 0 degree measurement is due north. So that's important when we're looking at this next problem. So an emergency call is made 5.6 miles from one cell tower and 2.7 miles from a second cell tower located 4 miles south of the first. State the two possible headings from the second cell tower for the location of the emergency call. Okay, I think it's always best in these cases to draw a picture, so let's do that first. So this is what we're talking about. We've got an emergency tower. We're calling it tower in the north, and then we have a tower in the south. And we're told that there's a 4-mile distance between the two of them. We're also told that the distress signal comes at a distance of 2.7 miles away from tower south and 5.6 miles away from tower north. And if you were to, again, do these to scale, that's what they're showing here with these arcs. If we were to use a compass from this position and cause it to sweep out a circle, we could say, well, if it's that distance, then that is the distance of the radius away from the distress call. And then we could do the same thing from the south tower, using a radius of 2.7, drawing a circle around that one. And then all we have to do is just see where do the circles intersect. And so in this case, we've already drawn it at the point of intersection. It would be one here, but it also could intersect here. And so we've called that the distress call in the east or the distress call in the west. Now, we don't know which one it is in this case, and so this is why you'll hear people talk about triangulating. So if we had a third tower that also gave us a measurement of distance, we would draw another circle, and then we would just see where all three circles intersect one another. And that would triangulate the position. But in this case, we can narrow it down to 2 positions. Okay, so in this case, notice what we've got now. We've got an angle theta, which is the bearing from the North Tower, right? Which is the way that we want our bearings to go. Remember, with the compass, in this case, we go down this direction whenever we're measuring the angle theta for the bearing. So this measurement, this angle right here, is the one that we want to discover. Okay, so if this is cosine theta, we use cosine theta, law of cosines here, and then plug in all the pertinent information. So we are here 4 squared plus 2.7 squared minus 5.6 squared, all divided by 2 times 4 times 2.7. And when you do that calculation in your calculator, you get negative 0.3736. We take the arc cosine of that, cosine to the negative 1, and you get 111.9 degrees, which again makes sense of our picture, right? Because if we were here, this would have been 90 degrees, and it appears that it is further down than that. Now that would be for this bearing out here for the east one, but we also have the potential of it being in the west. So what you need to realize here is that this, by similar angles here, this angle has to be congruent to this one. And if that's the case, then this measurement of this angle is just going to be, you see this 111? Well, we would just subtract 90 from that and get something like 21.9. And then we could, again, go take this angle, which would be all the way to 270, and we can subtract that from it. Or, if you prefer, we could say, okay, well, this angle has to be the same as this angle, this whole thing, so it's 111.9, and we just need to subtract that from 360 all the way around. So either way, you can get 248.1 degrees. So that would be if we were going all the way around to this bearing right here. Okay, one last thing to talk about in this chapter is we can now talk about developing a formula for areas of triangles. Now, I'm sure in geometry, or even maybe before that, you learned that the area of a triangle is 1/2 the base times the height. And that works great if you know the height. But what happens if there's a case in which you have a triangle where you don't know the height? How would you go about solving this? Well, in other problems that you've had before this, there's probably been some simple way to get at the height, but you don't always have that at your fingertips. So we're going to now show you that you can develop, there's a formula for areas of triangles where you don't know the height, where we know just 2 of the sides and the angle in between them. Notice here, this is again side, angle, side, where we know an angle within the 2 adjacent sides next to it. If we know that information, we can solve for the area of the triangle. And this is just shown to you how we can go about doing that. We can say sine of C, sine of this angle, is H over A, right? Opposite over adjacent. That's if we're doing this whole triangle here, the right triangle, okay? So we can also rewrite that as H equals A sine C. Well, if the area of the triangle is 1/2 base times height, and this would be the height of what this triangle would be, then we can substitute A sine C in for where the H is. And when we do that, we get this formula, 1/2 AB sine C. So notice, all we need to know is 2 sides and the angle in between them. And we can plug all of that into this formula and get the answer for the area of a triangle. So let's get some example doing that. This is exercise 2 on page 280. Notice what we've been given. A side, then an angle, and then the other side. So we have the information that we need. It's just 1/2 AB sine C. So we plugged it in. 1/2 times 6 times 3 times the sine of 95. Put that into your calculator. You get an answer of something like 8.966. So your book has a nice little chart showing you triangle area formulas. Again, write these all down. Put these into your onto your page with all of your formulas from this chapter. Area of a triangle is 1/2 base times height. Notice if we have side angle side, we just take 1/2 AB sine C, or 1/2 BC sine A, or 1/2 AC sine B, depending on which sides we're given. Just remember, you have to have a side, then the angle, and then another side. 2 sides next to each other with the angle in between them. Now, there's another formula on here to show you as well called Heron's formula, which involves knowing semi-perimeters and just the lengths of the sides. So this is the case where we don't know any angles, but we just know all the sides, or in other words, side, side, side. In that case, Heron's formula works to develop this. And the semi-perimeter that's talked about here with this S is just 1/2 the summation of the perimeter. Semi-perimeter, half of the perimeter. So you add A, B, and C together, you divide it by 2, and you plug that in for S in each of these spots, and then you plug in your A, B, C's appropriately as well. So we'll do an example of doing that as well. Okay, so here we go. We have find the area of a triangle PQR. Now, notice the problem here when we just look at this immediately. We have a side, we have an angle, and we have another side, but notice that the angle that we have is not the one we need. We need the one in between the two sides that we know. So how would we go about finding the angle that we don't know in order to then use that formula for area? Well, you'll make use of rules you already know. So for example, what if we use the law of sines? What if we use the law of sines here? Sine R over R equals sine Q over Q. Well, we have here the Q measurement for this angle, and we have Q. And then we'll call this R, and then this would be the R angle that we need to solve for. If we do that, we come to an answer of roughly 48.3 degrees. Now remember, that's now this angle, but we wanted this one. So how are we going to go about finding P? Well, we know that P has to equal, you should be really used to this by now, 180 minus Q minus R. So we just subtract the two other angles. That's a really long minus there. If we subtract the two other angles from 180, we'll get P. So 180 minus 56 minus 48.3 equals 75.7. And now that we know that this angle is 75.7 degrees, we now have a side and an angle and a side. So we can use now the formula 1/2 RQ sine P to solve for the area. We plug in all of those values and we get out 43.6 meters squared. Now, Heron's formula, which I already described to you in the previous slide, is this. Again, you have a box in your book that describes this. Let's do an example of using Heron's formula. It's pretty simple. So here we have a word problem, which makes it a little bit more fun, and kind of see a practical real-world application of this. So a developer desires to purchase a triangular lot with 1,100 feet of frontage on Main Street, 820 feet of frontage on Acadia Drive, and 638 feet of frontage on Rutherford Road. Calculate the acreage of the lot. Notice here that it tells us a conversion that 1 acre is equal to 43,560 square feet. Okay, well, let's think through this. So our formula is 1/2. We first need to find what the semi-perimeter is, which is just going to be 1/2 the sum of all three sides that we've been given. And so we discover that to be 1279. And then we just plug it into the formula. That 1279 goes here. It also goes here in each of these subtractions. And then notice we put each of the three sides in here. After all the subtractions are made, we then multiply all four of those numbers together and take the square root. And we get something like 259,536 square feet. We can then divide that by the 43,560 square feet in each acre. And we get a final answer of roughly 5.96 acres for the square footage of, or I'm sorry, the acreage of this lot. So what happens if it's not, though, a real triangle and you were to go about doing this? Remember our example from before. We know this is not a real triangle because this one side of 12 is longer than the sum of the other two sides, the 4 and the 3. What happens if we do that? Well, you'll put in for the semi-perimeter, you'd get something like 9.5. And then when you go about plugging it into all of this, notice what happens. This is fine. This will yield a positive number. This will yield a positive number. But notice here, this will yield a negative number. And when you take that negative number and you multiply it by 3 positive numbers, what are you going to get? Well, a negative times all the rest of this is going to make it negative. And so you're going to have a square root with a negative number underneath here. And what does that mean? Well, it's an imaginary number. In other words, it's not a real triangle. Okay, it's not a real triangle. You will not be able to get an answer. All right, so your homework is to read over 5.7. Just make sure you understand everything that I've talked about here today. And then complete numbers 2 through 28, 44 through 52, the evens on pages 280 and 281. Then, this is the last video of the week. You just have the 2 videos to watch. They are a little bit longer, but you can watch these 2 videos. Then later this week sometime, I want you to work on the Chapter 5 review. And I'm asking you to do every 4th question. So you pretty much have 3 assignments from me this week. You have the one from 5.6, the one here from 5.7, and then I want you to work the review problems at the end of Chapter 5 and do every 4th question. If those are easy for you, then great, you're done. If you feel like you need more practice, pick any section that you're struggling with and do some more problems around that question and see if they come a little bit easier. Again, if you guys need any help, please reach out to me. I'm more than happy to get on a Zoom call with you guys. Or talk to you through email or however I can be helpful. Next week on Monday, we will review everything that you've been doing, and we'll be preparing to try to take a test on Tuesday if at all possible. So please do let me know if you have questions, if you're struggling with any of this, or even any of the material before these couple of sections. This is a good week for you to review all of that. Make sure that you know what's going on and get ready for the test, which will take early next week. God bless you guys. See you soon.